of my students were in trouble. They were trying to cut a stick that was 75 centimeters long in half. So I said, well, what's half of 75? Long silence. Well, okay, what's half of 70? Another long silence. Okay, what's half of 80? One kid tentatively, 50? The second kid, with confidence, 60! The third kid busted out his iPhone to work out the problem. Now, this is not an isolated incident. Though I teach science instead of math, I frequently run into situations where kids, they may have been, well, I'm certain they were taught how to divide 80 into 2, and even how to divide 75 into 2. And they passed it on the test, but then it passed out of their working knowledge vocabulary. Their toolkit does not include something as simple as taking half of 80. And I think that this is the result of the way much of education goes. It's so test-focused on the short-term test, so we can get that out of the way and go to the next topic. Mathmagic Blocks is designed to provide a foundation, a strong foundation, upon which all higher math can be built. Without it, math is built on a bed of sand. The Swiss developmental psychologist Jean Piaget came up with a theory based upon years of research, interviewing and working with kids of different ages, a theory of cognitive development, which I think explains what the power of Mathmagic Blocks is to do good in the world. Basically, what he said is all human beings go through a series of steps as they develop their ability to understand the world and organize it. And there are a couple of interesting tenets to his theory. First of all, the steps are the same. It doesn't matter whether or not you're living in a tribe of Stone Age rainforest dwellers, or whether or not you're the son of a professor of mathematics at Columbia University living in Upper West Side Manhattan. The steps are always the same. Secondly, there's no skipping steps, and you can't hasten a step. Sure, you can teach a kid to memorize the way they're supposed to act for the next step, but it's not robust knowledge. They haven't got it, and it crumbles when you ask them to divide a stick in 2 that's 75 centimeters long. And the third thing that's really interesting to me is that any particular step can't fully understand another step. A child can be taught how to think like a formal operations thinker, which is what the adults of the world are, but they don't really get it. And in the same way, we as adults can see kids struggling, but we can't really believe that they don't really just get it, they're just being difficult or something. So all of these things come together in Mathmagic Blocks, because what happens is students get a chance to, with physical manipulation of the world, understand it at a level that they need to get. Because the initial stage that kids enter school at is called the pre-operational state. And what that means is operations that require mental manipulation, like addition, multiplication, division, and stuff, can't be done without physical manipulation of the world. And once they've done the physical manipulation, then they become capable, as they move up the steps, of being able to do it as a formal operations level. And that's the level that we're at. 2 times 3, 6, you just get it. But initially, it doesn't make sense. And when you memorize it, it still doesn't make sense. You just memorized your multiplication tables. A simple way to understand how pre-operational children, which is ages 3 to 7, see the world that's different from the way you and I see it is with cookie dough. I would challenge you to try this experiment next time you're making some cookies at home. Make 2 balls that are the same size as each other, and then make a small tidbit to tantalize your child. And invite them in and say, would you like some chocolate chip cookie dough? If they say yes, and they take your masterpiece in their mouth, they're a goner. Because once they've eaten that little piece, then you say, well, would you like some more? Of course, they'll say yes. And you say, well, I have 2 balls here. Which one's bigger? Well, either way you got them. If they say they're the same size, then just choose one. If they say that one's bigger, then choose the one that they say is the smaller one. So let's focus on the smaller one now. Now the smaller one, you're now going to take and you're going to transform it as in kindergarten, when you used to roll out clay and to make snakes, and you're going to take that same smaller one and keep on rolling it until it's way longer than the other one. And then ask your child, which one do you want? I'll bet you a set of mathematic blocks that your child will say, I want that one. It's bigger. It's more. Because at that pre-operational level, the concept of volume, length times width times height, has not been mastered. How can you multiply 2 length times 3 width? It's way beyond them. But more is shown because length is bigger, therefore chocolate chip cookie dough. Even though they saw you take the exact same volume. That's a simple example of how they don't understand things the way you and I do. And it's really important to appreciate the value of mathematic blocks, to believe that they're not making things difficult for you. They just see the world in a different way. And the foundational experience with manipulating the world that mathematic blocks gives provides a foundation that then makes a robust foundation that other higher level thinking skills can be mastered. Question for you. What's the difference between 2 and 2? Well, the answer is there's a big difference. Even though you as a formal operations thinker would say, oh, well, they're just the same thing. In fact, this represents 2. This is 2 objects, but this is a symbol, a squiggle that represents 2. And they're not the same thing. If you go back into the history of mathematics, it was not that 2 plus 2 equals 4 was the start. The start was just counting. Counting was essential for human survival. They had to be able to count how many sheep they had, how many wolves were up on the ridge looking hungrily down at them. So counting is far more fundamental than mathematical operations. And for that reason, it needs to be mastered first by understanding just what numbers are. So this block here is 2, but it's 2 in a different sense from the way this is 2. And for that reason, symbolism of the thing is something which kids need to master, and they will do that at the initial stages of playing with the black blocks. Students will catch up to the concept that too many blocks is too confusing. So let's start at the very beginning. 1 plus 2 equals 3.
Told you the word question. I found ways. I told them put a 3 and put a 2 and a 1, they'll balance. Oh, this is so fun. Get all the blacks and put them over here. Yes. Get the blacks. Pass me an 8. Give me. Got a 5. Give me 6. Wait. It's equal.
But after the kids have been playing with blocks for a while and heaping all the blocks they can onto the balance, there will be a certain level of frustration as they realize this is too complicated. I can't organize, I can't make sense of this. And the innate human drive to make sense of the world will be frustrated. At that point, they'll go back to just the simplest possible mathematical expression.
Oh my God. It's balanced with so many numbers. No. I know what's in here. They're beads.
2 is 2. It's the same thing. Now, there's a couple of points that need to be made here. 2 is 2, but not everything is 2. In fact, 2 is not equal to 3. So inequality, as well as equality, is implicit in playing with mathematic blocks. Now, there are different ways that you can take and get a number. For example, 5 is also not equal to 2. But inside of 5, there's a 2 and a 3. So you can kind of get across the concept of 5, the symbol actually represents other symbols. And not only does it equal 2 and 3, maybe baby's first equation, but there are other ways that you can break that 5 apart. For example, you could also take this combination, and that also would equal 5. And then the next leap up, of course, would be, well, you can have a combination that equals a combination. So students go up this ladder of understanding more and more complicated concepts. In this case, we have an equation with 4 terms in it. After playing with the simplest numbers, 1, 2, and 3, the other blocks are crying to be included in the fun. And so the rest of the black blocks can be used to understand addition, different combinations. But beware.
15 here. Wait. No, 18's bigger than 15 because they're both. You can add 3.
In this case, 15 and 18 are different by 3. And the kid cries out, oh, add a 3 in there. But what they don't realize is there's an entire new level of understanding lurking in the colored blocks.